Okay, so we've last day of chapter 16. Review next class. Excuse me. Review next class and then exam after that. So that would be what? Monday. Sound good? Okay, so we've seen this rainbow type thing earlier, but that was with rotational vibrational spectroscopy, right? But it looks really similar, right? And so I'm not really going to say much about it, but just realize that this is from a Raman spectrometer, so it's pretty much looks just like an FTIR, except there's a laser in there because they're looking at scattered radiation, and it's really much. It can detect a lot of different things that IR can't, and we'll we'll have some examples of that, but. We talked about IR active. Yeah, man, that'd be a good review. What's IR active mean? IR active what? What's IR active?
An oscillating
Dipole. Okay, of a what though? Of a what's something in the molecule of a vibration. Of vibration, right? Okay. So we've got a vibration going on, right? These molecules have vibrations, and like there's normal modes. We'll get into that. It's coming up, normal modes. But so molecules vibrating. If it's what is changing, ooh, it's Raman active too. It's oscillating dipole. That's true for. It's going to absorb infrared, if it's going to absorb heat. But what needs to be changing in this vibration if it's going to be Raman active? It starts with a P.
Polarity?
Close. Polarize. Ability. Polarizability is changing. Right. Polarizability is changing. Okay, so if we take a look, that's good enough. If we jump down to the next section, they're talking about normal modes. And we discussed before, I think, about whether a molecule is linear or not linear, how many vibrational modes there are. And they're just adding a word in front of that, normal modes. And they're trying to stress the fact that think of like a water molecule vibrating. Like this is the oxygen atom, and these are the hydrogens, right? It's undergoing this vibration, for example, right? Okay, there's so many different vibrations. Well, the idea of normal mode is that you can excite only this vibration, and not any of the other vibrations. Okay, so you can excite a normal mode, and it won't interact with any of the other vibrations. I think that what has to be going on, though, for that to happen is way up, where is it? Here. This normal mode idea works as long as you don't have this funky thing going on. What's the difference between this type of plot and this plot? It was the A word. Anharmonic. This anharmonic motion. If you don't have any anharmonicity, then you can excite one normal mode without exciting the other normal modes. And so so that's why funky things start happening when you start getting up in these higher energies. Okay, but that may be more information than you need, probably. Okay. Oh, I want to try something here. This symmetric stretch, anti-symmetric stretch. Well, we might as well jump up here first. Like the number of vibrations, remember this? It was 3n minus 5 and 3n minus 6. I think maybe I'm thinking instrumental. Didn't we talk about this in PChem? We didn't talk about this in PChem. It was instrumental. Okay, so this is the number of vibrations, number of normal modes. Okay. 3n minus 5 for what type of molecule? 3n minus 6 for what type of molecule? Do you remember this, my instrumental people?
One was for linear,
Yeah,
for nonlinear.
yeah, one was for linear, one was for nonlinear. So let's write linear on both. Which one was nonlinear? Yeah. Okay. So water, just to make sure you're following this, water has blank vibrations. How many?
No, wait, no, plug it.
Zero.
What does the capital N stand
Let's help them out. Instrumental people. What's the capital N stand for? No, yeah, this is really bad notation, isn't it? Let's just write, because that N looks like that N. That doesn't make sense. Let's call it big V. Okay, so the number of vibrations is big V. What's the big N stand for in the equation 3n minus 5 or 3n minus 6? The number of?
So the number of atoms?
Number of atoms. The number of atoms in that molecule.
3. Has 3 vibrations.
How did you get 3? You're right.
I get 3 too.
Because water is bent, so it's not linear.
Good.
So use the bottom half.
Okay. Exactly. So how do you know, though, that water is bent?
Vesper.
Close, not Vesper, but Vesper.
Wrong.
What did it stand for? This is a general chemistry thing. This is the only thing that we have to work with.
Valence, electron.
Valence Vesper. V-S-E-P-R. Valence, shell, electron, pair, repulsion theory. Electrons take up a lot of space. That's all it is. They just push everything around. The Sepper theory. Okay. So if we take a look, let's take a look at this. Carbon tetrachloride. Because I found this online. I haven't recorded it or anything, so I haven't stolen it from these guys yet, but I will. Okay, so here's nice carbon tetrachloride molecule, right? Everyone recognize it? Okay, hopefully you're still working. Are you still working? I got too many now. Okay, so here's a bunch of vibrations. Now what I want to see if you can predict is which of these modes are Raman active, which ones are IR active. Now I think the IR active one is much, much easier to predict. Would this be IR active? With this vibration, could you see it on the FTIR instrument? Is it going to give a peak at this wave number,
Yes.
460? Now, Alyssa said what it had to happen. What does this molecule have to exhibit in that vibration? Oscillating dipole. Does this exhibit an oscillating dipole? Yeah, it's every instant in time. If you took a picture of this, it's perfectly symmetric. This is not going to exhibit an oscillating dipole. This is IR invisible. And we're not supposed to say that. We're supposed to say it's IR inactive. This is IR inactive. How about this one? IR active? Yeah, Gloriana? You take any instant in time. Oh, that's a good question.
Are those supposed to be like
Looks like it would
towards
be.
and forward, like behind you?
B3 is IR active for sure, right?
Well, let's back up a little bit. Let's use some more words in here. Is this a symmetric stretch or an asymmetric stretch?
Symmetric.
Symmetric. Everything is in sync, right? Okay. They're all going out at the same time. How about this? Would this be a symmetric stretch or asymmetric stretch? think these, it's,
So like when this side goes down, this other side goes up.
yeah, it seems like they're both
This-
going in at the same time, right? We haven't answered whether this is IR active or not. We'll let the next button show us. It's kind of hard to tell because, right, this is kind of being, when this gets squeezed in, that one's being squeezed in. So, I don't know. How about, would this be IR active?
Yes.
Yeah, most definitely, right? This has some, what type of stretch? This is asymmetric. While this is getting compressed, these are getting longer. So that's asymmetric. Dang, this looks just like that, doesn't it?
No, but the
It's
top
already
one,
up and down.
the top one isn't moving.
Oh, this one isn't moving.
Yeah.
So would this be IR active?
Yes.
No. The top one's not moving, so wouldn't it be inactive?
No, the top one over there is inactive because they're symmetric.
Yeah, this is totally symmetric. So there's no changing dipole moment. Here, I would say this is IR active because this dipole moment isn't changing, but these are, and there's nothing to cancel out that change. I would guess. All right. So whether that's Raman active or not, you pretty much always guess yes. But we're going to attack that and how the homework will attack it. We'll show that in a little bit. Whether vibration's Raman active or not, we'll leave that for what's coming up. I think it's, well, let's see here.
Let's see.
Okay, so here's Raman. See, Raman sees pretty much everything. It did see everything,
Well, that doesn't count.
right? IR, man, it looks like IR. The only one it saw was this one.
Right. That had the most change.
Yeah. So these were all IR inactive. Wow, so this one was IR inactive. We were wrong. Okay. I don't know what all the rest of this stuff is. What is all this? Oh, okay. Okay, so that's good enough. I shouldn't have closed that. I'm trying to save that. Anyway, so we talked about symmetric stretch, asymmetric stretch. Let's try this one more time. I think I had some more of these. Yeah. How come it doesn't get any bigger?
Push the box at the top.
There it goes. Okay. Are any of these IR inactive? Whoop.
The second one.
And you're calling this the second one? This
third
one's not
one
even
too.
doing anything. I
The
think
third one also, right?
this one looks IR inactive to me.
Yeah, it's symmetric.
Yeah.
It says that there's symmetric stretching.
Yeah, but I guess that's true. But I guess that makes sense if it's a symmetric molecule in the first place. But otherwise, a symmetric stretch would be IR active. So don't let that get you. How about this one?
It is symmetric, right?
Is there an oscillating dipole?
They're the same length every time, it just bends up and down.
Yeah, so is there an oscillating dipole?
Oh, it's just bent then, right? It's just like water then?
It's bent, then it's linear, then it's bent.
So it's active?
I'd say there's an oscillating dipole here, right? That only when it's linear, only when it has this shape, I mean, now there's no dipole. And then, right, they could perfectly cancel out. But then once this guy moves a little bit, there's a dipole, and then there's a dipole, goes to 0, right? So I think there's an oscillating dipole here. How about this one?
Yes.
Yeah, definitely. Okay. What was this? Same thing, isn't it?
No, that one's different. Yeah.
Oh, one thing that I don't know if you noticed is that this 3n minus 5, 3n minus 6 thing, that's the total number of vibrations. But by symmetry, some of those vibrations are exactly the same. Like, we've seen this before, it's going in a different plane. So they're just degenerate. They're all going to give rise to the same peak. Okay, even though you have, so if you think you have 9 vibrations, well, you should see 9 peaks. No, because a lot of vibrations are the same due to symmetry. Okay. So IR active. Yes. IR active. Isn't that weird? But it's that dipole is changing though, right? I don't see him being canceled out. IR active? I think so. Okay. Bless you.
Thank you.
Force field. I picture that as kind of like you have that vibration going on, but first you transpose all this. What are K's? Force constant, right, from that spring. So make them different numbers, right? I guess start. So if these are all the same, then it's the same force field everywhere, wherever those atoms are moving to. So if you make some constants bigger, well, now it's right. Now the force has to be bigger for it to move in that direction. So it's kind of what they're picturing when they say a force field. That is a 3-dimensional array of these force constants. Okay. What's tumbling? You gymnast, volleyball player. What's tumbling? Yeah, rolling around. Is it random?
I was like doing a question.
No, it's a PChem. It's a PChem word. Who knew? Right? Is it random?
No, it's ordered.
You're tumbling.
It's like random.
I'd say it's really random, right? You're tumbling.
Right.
All right. So just random motion there. Random changing orientation. Parallel band and perpendicular band. Okay, so let's say you have a couple of these. Let's go back to CO2. Did I delete it? I think I did. I want this to be symmetric. Where is CO2? Okay. So take a look at this. So we're supposed to be talking about parallel band and perpendicular bands. They're just peaks in the IR spectrum. And this oscillating dipole, everyone agrees there's an oscillating dipole here, right? Okay, is this oscillating, before I say that, we can't avoid it. The poor people who didn't take inorganic. Who took inorganic? Okay, Gloriana, tell Jeffrey what a principal axis is. Like principal axis of rotation. And using this molecule. Where is a principal axis? Where is the principal axis of rotation?
Isn't that where a
In this
molecule can
molecule.
rotate? Well, you split it in half.
Yeah, molecule can rotate and because not reflecting. So the splitting in half, that's reflection. We're talking about rotating.
Oh, like if it can rotate in a whole degree?
It can rotate 10 degrees, 20 degrees, 30 degrees, whatever, and it looks exactly the same. Okay, so, and there's a lot of, like for example, I could take right down the center here and rotate it how many degrees? 180, and look exactly the same, right, Jeffrey? Look exactly the same. Okay, how many degrees, Jeffrey, in a circle?
360.
360. All right, I rotated this by how many degrees to get the same thing? 180. What's 360 divided by 180? They call this a C2 axis. That's how they get these numbers. They take 360 divided by the angle that you're rotating it to get the exact same thing, and that's the principal axis. And they give it a little symbol C or something, but who cares? The point is that's a principal axis. Now, the principal axis, no, I guess we have to talk about the notation. So they call it a big C with a little 2. But that's not the principal axis. The principal axis is the one that has the biggest subscript. So you can look at this molecule. It's kind of a trick question with this molecule. But there is a C with a bigger number than 2. for this molecule? In fact, it's going to be C what?
4.
Is it C infinity?
C.
Because if you go straight through.
C infinity. C infinity, right? Because it's no matter what the degree is, you can rotate. So it's kind of a trick question.
So like
We should have picked a better one.
Yeah, we
But anyway,
complicated.
this is C infinity goes right through the center. There's not a big number bigger than infinity, so that is the principal axis. Okay, so we're supposed to be talking about this parallel band. So some of these vibrations are IR active, others are IR inactive. So the ones that are IR active, they're either parallel or perpendicular bands. So if this motion, right, this oscillating dipole, is this dipole oscillating parallel to the principal axis, or is it oscillating perpendicular to the principal axis? In this one right here. Our principal axis is going through here. It's oscillating parallel. So this would give rise to a what band? A parallel band. Right? Okay. IR active or IR inactive?
Active.
IR active? Each instant in time. Remember, this is carbon and those two are oxygens. Each instant in time, the dipoles are perfectly
Symmetrical.
canceling out.
This is inactive.
So this is IR inactive. So can we talk about parallel bands and perpendicular bands? No, there's no peak to talk about. So it's not going to give rise to a band. It's IR inactive. Okay.
Oh, that one's the
So IR active or IR inactive? IR active. Perpendicular band or parallel band?
perpendicular.
Perpendicular, because the motion is, the oscillating dipole is oscillating perpendicular to the principal axis. Yeah. So that's a lot of verbiage just to describe parallel and perpendicular bands, right? Okay. I think you're going to see this. This is going to be useful in the homework because we'll take a look at it. But I'm trying to remember the homework, and I remember they're talking about, is this vibration IR active? Is it Raman active? And that sort of thing. Well, the only way to really tell, well, it's Raman active if that what is changing during the vibration? Polarizability. Right. So how do you know? That's a very difficult, I mean, if you had a little Spartan thing going, you could tell. So this is really the way that the book, every homework question is oriented so that you can answer whether something's Raman active or not with this exclusion rule. So they're going to ask you about only molecules that have a, what is the center of symmetry, my inorganic chemistry people? Yeah, that was a little simple for it. That might help, but did carbon tetrachloride have a center of symmetry?
Yes.
I lost it. Dang it.
You closed out
Well,
one of them.
the open recent little 3 dashes. Over right.
Where?
Very, very right. Right. More. Right there. No, right there.
This?
Yeah,
Yes.
hit that, and then recent tabs.
Oh, that is so useful. Oh, man, I wish I would have known that a long time ago.
Let's go to your history.
Yeah. Where'd you go recent?
Yeah.
I want the earlier one, though.
Click the 4
Click that
tabs.
one.
This. Okay, there's carbon tetrachloride. Does it have a center of symmetry?
Yes.
And tell Jeffrey how you know that.
This is the same molecule around the carbon.
Not molecule, same
Atom.
atom.
Carbon.
You reflect through the
Principal axis.
center, right? Take an atom and reflect through the center. Do you see it on the other side?
Yeah.
No.
Well, I don't, do you? That means there has to be a yellow ball directly over here. So does this have a center of symmetry? No. So you're not going to have any questions on this in the homework.
Yay.
So, where's one that has a center of symmetry? I had a nice picture of,
Bipyramids, those have symmetry, don't they?
oh yeah, I guess we could draw one, right? Can I draw one?
It was so hard. Dr. McGill made it really hard.
Flashback to Jen Kim and Oak.
Let's draw one. Okay. Oh, I see what you're, oh yeah, I know what you're talking about. Okay.
Like sulfur hexafluoride.
Yes, that's what I was thinking. If you did SF6, you go through the separ theory, count up the whole all the lone pairs and everything, right? The first atom always goes in the center, right? And then you're surrounding it with 6 objects. There's no lone pairs once you do the separ theory. What do they call it? It's a what dot formula? Lewis electron dot formula, right? So you do that. So it would end up looking like this. If you did it following all the rules. This again is more information than you need because I don't think the homework's going to have you do this. It's supposed to be an F. Okay, and there's no lone pairs on the S. So what you're supposed to do, this is how I did it. Ah! Can't count. Thank you. There's 6 things. Now, this doesn't look 3-dimensional at all. It looks like a pancake. So what you're supposed to have done is this is how I did it in Gen Chem. What I said is, hey, how many things are surrounding the S? There's 6, right? 6 things. So the shape that you were supposed to have memorized was when you draw 6 objects. There it is. The dashed lines meant it's going straight back. It's really not straight back. They're kind of out at an angle, right? And then the wedges, this is called a wedge. It meant that it was coming towards you, out towards you, right? So this is a straight line. Right here, this is a straight line. Whoop. Why doesn't that activate? This is a straight line here, right? That's a straight line. So and then the solid lines meant in the plane of the paper, plane of the paper. So this object drawn 3-dimensionally is this. Where's sulfur in this mess, Jeffrey?
In the center.
In the very center, right? So you put all your F's in. Some people like to draw the S, the sulfur, but you don't need it. Okay, does this have a center of symmetry? Yes, because you take every atom, reflect through the center, and then you see that same atom. Right, so this has a center of symmetry. If I replace one of these with, I don't know, Cl, now I've lost it. No more center of symmetry. Okay. So what you're supposed to do to answer these questions, again, long story, is a vibration Raman active or not? Pretty much every homework question is going to give you a molecule with a center of symmetry. Otherwise, this exclusion rule doesn't apply. So a normal mode, a vibrational mode, cannot be both infrared and Raman active. So you look at this vibration of this molecule. It has a center of symmetry. If it's IR active, then it has to be Raman inactive. If this vibration, if the molecule has a center of symmetry, this normal mode of vibration is Raman active, has to be infrared inactive. That's the exclusion rule. So that's how you rule in or out this Raman activity of vibrations. That's how the homework has had me do it. Apply the exclusion rule. Depolarization. Okay, this, see how they have scattered radiation here? What's this green stuff going up and down? What's that green stuff going up and down? Light is composed of what 2 fields? Well, the whole thing is electromagnetic. Elec
Electric and magnetic.
electric magnetic. That's why it's electromagnetic, right? Electric and magnetic. So they're only illustrating which one? The electric field. So the big green thing is the what radiation?
Scattered.
Well, scattered, it's going to be the incident, right? Because you need a lot, you need like a laser, something really bright, very highly intense. Amplitude is huge, right? And then you get a scattered event. So your molecule's got to be in here somewhere, okay? And they're only showing the electric field is what I'm getting at. And this whole polarization thing, you can get a lot of information out of how is this molecule oriented in this DNA helix, and what is it doing there? What is its residence time? You can glean a lot of information just by seeing how polarized or unpolarized scattered radiation is from a chemical system. So this is just the bare fundamentals, not even looking at the applications of it. But I think the applications are more interesting than what's going on here. But so your incident radiation is, right, electric field is the big green mess. Your scattered radiation is observed 90 degrees out. That's how all these Raman, they're trying to illustrate a Raman spectrometer event. That's what they're trying to do here. They're trying to show you a Raman spectroscopy event, okay? And how you have intensity that's, you see the little line there? This is I parallel. So I stands for intensity. So the intensity of the light that's in parallel to that incident radiation. And then you have intensity, and they didn't draw this one. They just drew a sinusoidal curve. Then they have I perpendicular. So the intensity that's perpendicular to it. So you measure those two. Pretty much all you do is just have a little polarizer in front of your detector and rotate it. It's really easy to do, and you can get these polarization ratios. Okay. I think if it was greater than, it's supposed to be a greater than sign. If that's greater than 0.75, they call it depolarized radiation. All right. Less than 0.75, polarized. That sounds way too much that you need to know. But anyway, that's where this stuff is coming from. They can glean a lot of information to these, without even doing this X-ray crystallography of these complex systems. They can get a clue as to what's going on. And then you can enhance this if this incident radiation, if the frequency of that incident radiation is the same as an absorbance frequency, then they don't call it Raman spectroscopy, they call it resonance Raman. So all of that they're doing is that they pick two energy levels, and the incident radiation is that frequency between those energy levels. And then you get enhanced scattering. And they call it resonance Raman spectroscopy. And that's kind of what this instrument is. Okay. Cars. Use 2 laser beams. So I'm not really going to say much about that. So, oh, shoot. Now looking at this homework though, this is a chapter 15 question. That's a chapter 15 question. So I'll take a look at it and see how ugly that is. But you pretty much have to use character tables, and I think we'll just have to omit that. Unless you've had inorganic chemistry, then you're expected to know it.
It was a while back. Oh, so we're not doing this one?
Yeah. Man, this is all you have for homework?
Yeah. You want to eliminate
Jeez.
Gotta study too, you have a test coming up.
Yeah, Dr. Smith.
Yeah, this is very true.
Yeah, Dr. Smith.
Well, that was like a long
So.
Smith cares.
Smith cares.
He cares.